Okay, hello and welcome to Fluid Mechanics. This is Class 1, Video 1. We're going to cover a bunch of topics. I'll make a bunch of different videos so they aren't too long, hopefully. In this video, we're going to cover the introduction material, talk a little bit about the brief history of fluid mechanics, and I think that's it. I think the next video we will cover the no-slip condition, classification of fluid flows, and maybe talk about the system and control volume. Then I'll make another video with the importance of dimensions and units, which has an example, and that's going to be the video that probably will matter the most to you because I think homework will have some of that inside it. And I'll talk a little bit, maybe I'll make a separate video for the modeling of engineering, problem solving technique, engineering software packages, which isn't going to be very long, and accuracy, precision, and significant digits. So there's going to be several videos. It's up to you whether you want to watch them or not as part of our class, but hopefully this will be also useful to other people, as I will probably also put it up on YouTube. So here's the introduction. I taught this class at the Coast Guard Academy, I think about 4 times, and one of my fellow instructors kind of encouraged me to take some of the doodling that I was doing and use it for some purpose. So I created a cartoon character, Wedded, and his buddy Vapes for fluid mechanics, and they are the fluid mechanics. And the features here, some of the hilarity are that this water droplet, Wetted, and his name's Wet Ted. See, my name is Ted, so that's why that's funny. And he's wearing like shower clogs, shower thongs, and he's got a pool of water around him. He's got, like, I call them hamburger helper hands, or like SpongeBob SquarePants hands. And he's got his buddy Vapes, who he's a floating little cloud. I named him Vapes because at the time, it was like 2015. So like a lot of people were vaping, a lot of, especially cadets, I would see them vaping, making huge clouds, huge vapor clouds with things. I think they've been discouraged from doing that now. But anyway, originally I was going to make this wrench a talking wrench because he's the mechanic, right? But he's a fluid mechanic anyway. But I think Wedded and Vapes kind of worked out well. And some of the idea behind these is that I can make some kind of silly drawing and capture like a concept, and maybe from it being an absurd thing that you would like remember it better, like this one right here. The idea behind this is that fluids can't sustain shear forces, right? So the definition of fluids can be found from this image, right? Or maybe that you remember, like the shears, scissors, shears, and fluids can't sustain that shear force. Or an image like this, where I'm showing the difference between incompressible and compressible liquids, right? Or fluids, I should say. Liquids are incompressible while gases are compressible. So anyway, let's start out with the big idea here. In the introduction, we should ask this question: what is a fluid? And I have this image. So I'm going to switch over to my notes. And these are notes that are provided so that you can more efficiently take notes. Like I'll put images and kind of as a framework and that kind of thing. So I'll often use these in class. At least I do in some classes. We'll see how this one goes. I think that's what I'll do. So just as a interesting question, kind of a basic question: what is a fluid? And I think the easiest to say what it's not, right? So a fluid is either the liquid or gas phase. But what we know it's not is the not solid phase, right? So you have 3 phases if you don't include plasma. And so the fluids are the liquids and the gases, so they're not solid. So it's a good idea we should compare them. What we could say for sure right here, these fluids, we'll say what is the difference, what is the difference between a liquid and gas and a solid? Like what makes something a fluid different from a solid? And that is that fluids can't sustain a shear. And I write too slowly, especially at the beginning of the semester, because I've had a whole summer for not writing anything down, and my chicken scratch gets worse. Cannot sustain a shear. load. Let's say a shear load or shear stress, shear force, whatever. And here's my little image that comes in right here. So I'll explain that down here in a second with this little drawing right here to try to help encapsulate what's that idea I can't sustain shear. I mean, what does that physically mean? But let's take a look and make some compares and some contrasts. So here's an image of the molecular structure of a solid compared to a liquid, and they show little arrows going every which way, and then a gas, right? And some of this is very basic stuff that you probably know really well. But let's just take a look and think about it. And think in terms of the molecular structure here. So one thing about a solid, these are densely packed molecules. I don't know if I'm going to write the word molecules out of the right. And I wish I had moved that over to the left a little bit because I wanted more space in the middle to go underneath there for it. Whatever. I'll try to remember to do that. And we have large intermolecular forces. I could probably just make this a PowerPoint and I just bring up these words because what are you going to do? But anyway, and well, if we have up here that this cannot sustain a shear, this can sustain a shear, And what do we mean by that? Well, let's go down to this little image right here. All right, so if we had these two plates and we, let's say we glue some rubber onto it, and this is, let's pick the solid phase of rubber, right? So if this is a solid piece of rubber, a solid phase of rubber, and it's glued to this bottom plate, which is stationary, and we apply a force onto here, as long as we don't exceed a certain limit to the strength of this rubber, it will come to equilibrium at some point, right? We would move it and it would stay fixed, right? So that is the shear, okay, because we're putting it in the plane, so that's a shear force that's being played in there, you know, and you could say, well, whatever the cross-sectional area is, here's the shear stress. The force divided by the area is going to be that shear stress that's going to be applied to this thing, and it will balance it out. But now, instead, if it was liquid, no matter what, even if it was the goopiest liquid that you've ever experienced, if it was in its liquid phase, if you apply a force to this, it will continue to move. It might even accelerate, but it will continue to move if it's a liquid. So that is what it means by sustaining a shear. A solid, which the solid form of rubber, can go into an equilibrium and sustain a shear load. Now I don't have enough room to write here with the liquids here. Let's look a little what a liquid is here. So now we could compare also compare the liquids and gases to each other. We have more molecular space or molecular freedom. Let's go down here. We also we know that the liquid easily deforms. One thing about liquid is not easily compressed. It can compress a little bit, and we'll look at that, I think, in the next class. Just like a solid, you know, we can actually compress it. We know, but it takes a large amount of force to produce even just a small amount of deformation. You wouldn't even be able to see in most solids, you know, what the deformation is when you apply a force, but you do know that, like, if it's steel or something like that, you know, it will deform, but it's not going to be very obvious until there's a really large amount of force. Same kind of thing kind of true with a liquid. It can, but we could basically consider it incompressible for the most part. One thing about a liquid that's different from all the others, it can be poured or pumped. And you can't say that about either a solid or a gas. And another thing about it that's special about it, it forms a free surface. Especially if there's gravity involved, right? So we have this, what we call a free surface right here. Compared to gas, I mean, if you try to put a gas into a container, it's not going to stay in the container unless it has a lid to it. And what we have with the gas is we have very large molecular spaces. The molecules are very far apart from each other. Molecular spaces. Wow, that was terrible. And there's negligible. There's an I in there. Negligible intermolecular forces. It's going to make this video too long by writing all this stuff down, right? I should just have it as a PowerPoint, but PowerPoint's boring. But is this any better? I don't know. The gas completely fills the container. That's why I have that little picture down there. And it's pretty easy to compress it. Okay, so those are like the big things that I wanted to mention. I probably won't take this much time in class. Maybe I will make it into a PowerPoint, make this. I mean, I don't know if I see the benefit of writing all that stuff down all the time it takes. But anyway, let's see how, because we're 11 minutes into this. I don't want to make a video that long. So we define what a fluid is. Let's say what fluid mechanics are and what they're used for, applications. I have a couple things to look up in there. But first, I would say that we take a look at the name, right? We've already established we have the fluids are liquid and gases. In mechanics, is there statics and dynamics, which you just took last year, right? And remember that dynamics is broken up into kinematics and kinetics. And remember, kinematics just describes the motion, while kinetics is the cause and effect, right? F equals ma. Right here, where we just figure out where position, velocity, acceleration, and time, how they're related to each other, and we just describe what we see, and we don't know why it moves that way. We just kind of observe and quantify. Here in kinetics, we actually get down to why is this thing moving. So in its heart, we have Newton's second law, but also we might use work and energy, or we might use impulse and momentum, but those are the kinetics. All right, so the big thing that we want to do, all right, there's many different aspects, but at the heart of fluid mechanics is trying to find a relationship between pressure, which we can think of as a force, right? Just force over area is pressure, and flow, which we can also think of as velocity, because we describe how the velocity of particles are moving, and if we have the velocity times the area, that's actually the volume flow rate, right? So we have a flow rate, but if we can find a relationship between pressure and flow, we can find out a lot of what we need to do with fluid mechanics. And the big equation we will go to for lots of stuff, but it has a limited application. It has some limits to how you can use it, but the really big guy is named Bernoulli. He is the most important equation. But he doesn't include viscous forces. If you include those, that becomes the Navier-Stokes equations. And you can hear, so these are really big, important equation names, but the one that's most useful to us, but we could accidentally abuse, so we have to be careful, is Bernoulli. And he's going to be the answer to most things. But for other applications here, I'm not going to write down the list. Remember that we have hydrodynamics, right? So that's going to be with like boats and stuff. So let me go back to this right here. So into the applications. This looks like it might be a heart, an artificial heart right here. That'd be kind of cool. Niagara Falls right here. Here's some fluids, right? In power plants, in the piping systems and stuff. Boats and waves, how the waves work. That's this is fluid mechanics. We can study that. We can also see the resistance of motion that the water causes. So that's hydrodynamics. We also have aerodynamics on aircraft and spacecraft. Within the human body, the flow of fluids, especially blood. Cars have aerodynamics as well. But they also, inside the engine, there's some fluids taking place, moving around. Wind turbines is a really important thing. Piping and plumbing systems. I did a lot of this as my undergraduate with some marine engineering, and I spent a lot of time on ships, and you wouldn't imagine all the pipes and valves in industrial applications. Actually, this looks a lot like what engine room, except not as clean and pretty. They're showing some of the history. All right, so we're just talking about some of the history here. I'm at 15-minute mark, 16-minute mark. I think I might want to wrap it up. So I'm going to go for video 2 here and the next one. So we'll conclude. Talk to you soon.